In this video, we're just going to take a look at some vector fields and decide if they're conservative by testing to see if they're the gradient of some scalar function. There's other ways to check and see if a vector field is conservative, which we'll discuss in a different video. But today we're just gonna try and get a scalar function. So is there a function f of x comma y, which equals some stuff over here, such that the gradient of f would equal f of x comma y? That's what we're hoping for. We want this to be true. Okay, so remember, a gradient vector, by definition, it's the partial derivative of f with respect to x, and the partial derivative of f with respect to y, and there might be more components if needed. In this case, we just have two variables. So, all right, so this thing here should have been the partial derivative of f with respect to x. So, f of x comma y would have to have in it a 1/2 x squared, and would also have to have a minus xy. Now, it's fun to just check and see why that's true. So just take the derivative of this thing with respect to x. So if we did partial f, partial x here, we would get x minus, and if x is the variable, then y is a constant, so the derivative is just x minus y. So this indeed works the way we want it to. Now, the question is, does this thing now have the proper derivative with respect to y? Because we need to derive that with respect to y to equal x minus 2, because this should be partial f partial y. So, and we know for a fact it has to have all this stuff in it to have the correct partial derivative with respect to x. So let's take the derivative of this thing with respect to y and see what we get. We would get 0, and then over here minus x, because this y is the variable, the coefficient is just negative x. That's just negative x. Unfortunately, if we look up here, that doesn't work. This is a positive x, so that's why it's out. Someone might say, you're missing this negative 2. That's a problem. We could actually capture that if we had made the function f of x comma y equals 1/2 x squared minus xy minus 2y. So you'll notice that, trying to use lots of different colors here, why not? That this thing here and this thing here are the same. That's needed, so we have the proper derivative with respect to x. This would give us an extra minus 2 here. So it would almost work, except for that negative in front of the x, which is not up here. So unfortunately, that means that this vector field, we can say this. Let's go to a new page here. F of x comma y equals x minus y times I plus x minus 2 times j is not conservative. So in other words, it's not path independent. So that just means if you're doing line integrals, say you're doing a line integral of this function f of x, y, I'll write it f of r of t dot r prime of t dt, and maybe we're going from the point 0, 0 over to the point 2, 4, then depending on the path you take, you'll get a different answer. So in other words, if we were to just think about going from 0, 0 up to the point 2, 4, well, we could take a parabola there, y equals x squared, or we could take a straight line if we want. And my comment is that since the vector field is not conservative, these two line integrals will have different values. If they'd been conservative, then the fact that they start and end at the same point would have made the two line integrals the same. So there you have it. Okay, let's take a look at another example. So I'll go to a new page. So let's consider this function here. Suppose I have f of x comma y is equal to the vector function 1 minus y e to the negative x, and we'll say I, plus e to the negative x j. And so the question is, can we find a scalar function that would have partial f partial x here, and then also it's got to have this partial f partial y. So here we go. Let's let it be f of x comma y equals, and I tend to start just with f. I want to have the correct derivative with respect to x. So I know I would need to have an x because that would give me the 1. And then to get this thing as a derivative, if I had plus y e to the negative x, that would do it. Because if I take the derivative of this, the derivative of e to the x is e to the x times negative 1. And then I multiply that by y, I get the negative y that's up here. So that actually works. Okay, now what I always hope is that this thing I have has the proper derivative with respect to y without having to do any more work. So I'm just going to check that. If I do partial f partial y, then I'll get the derivative of x, this x component, is 0. And the derivative of this component with respect to y, well, if y is the variable, the e to the negative x is just a coefficient, so the derivative is just e to the negative x. But that's exactly what I wanted. So this problem's actually done. This is a function, and what's interesting about this function, if I take the gradient of it, I end up getting this vector function. So this vector field, what we can say is, this vector field up here is conservative. All right, it's path independent. Sometimes you might even see a textbook or a talk where they say that it's fair, a fair vector field. Like take any path you want, it's the same amount of work. That's sometimes what people will say. Okay, let's take a look at one more problem. So let's consider a vector field where we have 3 variables. And so the first part is going to be 2xz plus y squared times I. Then we're going to have plus 2xy times j. Then finally, we're going to have plus x squared plus 3z squared k. So there you have it. Okay, so we're looking for a scalar function such that the gradient of this function, f, will just equal this vector function here. That's what we're hoping for. All right, so it's going to have this be partial f partial x. This part's going to have to be partial f partial y. And this part's going to have to be partial f partial z. Okay, so for partial f partial x, I know I would have to have an x squared z to get this first term. And then I would have to have a plus xy squared to get the second term, because the derivative of xy squared would just be x, sorry, 2xy, because, I'm sorry, that's not true, just y squared, because if x is the variable, y squared is just a coefficient. And the first term, x squared z here, if I take the derivative of that, the 2 comes down in front, I get 2x times z, which is just a constant, a coefficient. All right, let's check and see if this thing has the proper derivative with respect to y. It does, because the derivative of this term will go to 0, and the derivative of that term will be 2xy, which is exactly what we wanted up here. So you can see that. Okay. Finally, does it have the correct derivative with respect to z? Well, if I take the derivative of the first term with respect to z, I get the x squared. And I'm happy to see that because that's right here. If I take the derivative of the second term with respect to z, I get 0, which does not match the 3z squared. So if I want to have this derivative of 3z squared appear, there must have been at the end of this a plus z to the third, because the derivative of z to the third would be plus 3z squared, which is this thing. So actually, that's it. We now have our scalar function. We can say that f of x comma y comma z is x squared plus x squared z plus xy squared plus z to the third. It's coming from that line up there. And since we're able to do this, then we can go back and say that this vector field is conservative. And that would just make your line integrals much easier to calculate, right? You could just evaluate the scalar function at the endpoints, subtract that, and get the whole value of the line integral. Okay, I think that's a good place to stop. Thanks for watching.